Okay, we should be live. We should be live. Okay, I'm losing my voice. That's not good. Well, luckily, we have some new hosts, presenters.
So, you know how bionichaos.com is developed with AI? So, you know how bionichaos.com.
It's funny how it has this awkward pause at the end. I guess the actual sentence was too short. Need to aim at anything that is exactly 8 seconds or something. Well, also because you only get whatever 1,000 credits per month, and a generation with VO3 is 100 credits, so you can do only 10 of those per month essentially, unless you pay some gazillions.
Are now just.
Okay, so we'll actually be popping it into a standalone video. We haven't done this before. You have to bear with me. Hopefully we have some questions as well. We're doing this live stream so they are more interactive. But that's okay. If there is no human to talk to, we have these guys. This actually might crash my stream or something. Oh no, that was fine. Yeah, I had that awkward pause in the end. And it's 24 FPS only at 720p. Because you can download at the higher resolution, but then the sound goes away. So that's not good, is it?
Simulations are now.
So we have that one as well. And we should have the third one. Yeah, I have to download the original size. Problem.
Really, who needs human oversight when the machine.
that video go? I just want to download the third video. Bow. Ah, yeah. Now we are getting somewhere. Okay, so we have like 24 seconds all up. It's asking us to switch. So yeah, it's only 24 frames per second. Well, yeah, we'll have to switch.
So, you know how BioniChaos.com is developed with AI?
Well, apparently those biomedical data simulations are now just popping into existence all by themselves. Really, who needs human oversight when the machines are so creatively chaotic with our health data?
And the last one is walking away. Should we have some of the awkward pose?
So, you know how BioniChaos.com is developed with AI?
Well, apparently those biomedical data simulations are now just popping into existence all by themselves. Really, who needs human oversight when the machines are so creatively chaotic with our health data?
Okay, that's pretty good. Problem is, yeah, when they got 22 seconds. Well, I mean, if it's a high quality, then it's not a problem. You can generate more. But then we render it. Render. Well, that was quick.
So, you know how BioniChaos.com is developed with AI?
Well, apparently those biomedical data simulations are now just popping into existence all by themselves. Really, who needs human oversight when the machines are so creatively chaotic with our health data?
Do we need to increase the volume or something? Yeah, the volume seems a bit too low. Let's do 4.5. Speech normalization.
So, you know how BioniChaos.
Oops, that might be too loud. Okay, maybe it was okay before. Yes, we have new AI presenters. How about that? It's only 3.5 megabyte. So we have 3 new employees. VO1, VO2, and VO3. Well, we haven't actually used VO1 or 2. Best of all, VO3. Okay, I'll pop it onto LinkedIn. Okay. So we have 3. We have new employees at Bionic Chaos, VO1, VO2, and best of all, VO3.
So, you know how BioniChaos.com is developed with AI?
Well, apparently those biomedical data simulations are now just popping into existence all by themselves. Really, who needs human oversight when the machines are so creatively chaotic with our health data?
Yeah, I like.
So, you know how BioniChaos...
Okay, we're not looping this. That's pretty impressive what it can do. So thanks to Google Labs for providing this video. It's only 20 seconds though, so. Well, we have another 2 employees as the 2 guys from Notebook LM. Notebook LM. Okay, let's actually jump into development. So everything we do eventually appears on this side. Do we need a disclaimer? I think we might need a disclaimer. Unfortunately, let's use Okay, Notebook 11 is not saving chats, which is weird. You have to save them to Note. You have to save them to Note or something for them to be saved, is there?
Just so you know, all the content you're seeing here, the analysis, visuals, and everything else is generated by me, Gemini, version 2.5 Pro to be exact. As an AI, I work hard to provide accurate and helpful information. However, it's important to understand that the Biomedical takes no responsibility for any mistakes, damages, or issues that might arise from using this information, and that unfortunately includes even the worst-case scenario of data loss. So, while I hope you find this interesting, it's always smart to verify anything critical on your end. And by the way, pretty much everything we do and create here is also available over on our website, bionichaos.com. Definitely go check it out when you have a moment, and I'd love to hear what you think.
Okay, welcome back to the deep dive.
Glad to be here.
So we've pulled together this really fascinating stack of sources for you today, all about how we peek inside, that amazing mystery upstairs the brain.
Mm-hmm.
We're doing a deep dive into neurological tools, concepts,
Yeah.
focusing quite a bit on EEG and brain-computer interfaces, or BCIs.
Right. Think of it as looking at the brain's electrical language and the incredible ways, sometimes kind of messy ways, we've learned to measure it,
And visualize it.
visualize it, yeah, and even try to interact with it, talk back, like you said.
And it's a wild mix we've got here.
Mm-hmm.
We're going from, like, the really fundamental challenges, nearly 100 years old, just getting a good signal.
Yeah, but the basic.
All the way to this futuristic AI stuff, decoding thoughts, interfaces, changing what humans can do.
But it's not all smooth sailing. The sources definitely hit on the practical reality, too. The tricky bits, the stuff researchers and doctors deal with every day.
And some pretty big ethical questions hanging over it all.
Absolutely. So it's about understanding the how we study the brain, the amazing things we're finding, but also grappling with the should we as this tech just races ahead.
Sounds like a plan. We'll unpack these sources, find those critical nuggets, maybe bust a few myths.
Let's do it.
Okay, so let's start at square one, the grandmother of non-invasive brain measurement, EEG.
Electroencephalography, EEG. Yeah, the sources celebrate its 100-year history. It really is a foundational tool in neuroscience.
So what is it, basically?
At its heart, it's listening to the tiny electrical whispers from billions of neurons chatting away. We pick those up with electrodes placed on the scalp.
Right, the classic cap with all the wires. But
Yeah.
just sticking those on, apparently way more complex than it looks. The sources jump right into the nuances of impedance. Why is that such a big deal?
Ah, impedance. Okay, imagine you're trying to tune in a really faint radio station,
Okay.
but the connection between your antenna and the radio is loose. It's crackly.
Yeah, you get static.
Exactly. Impedance in EEG is kind of similar. It's the opposition the signal faces going from the brain through your scalp to the electrode. If that impedance is too high, or it's really different between electrodes,
You get static. A bad signal.
you get a weak, noisy, unreliable signal, like trying to read a book where half the words are just smudged out.
Ah,
So getting that impedance low and keeping it consistent across all the electrodes, carefully prepping the skin, using conductive gel, checking the contacts, it's maybe the most critical step. And honestly, kind of tedious, but essential for good data, even with the fanciest systems now.
So signal quality starts right there at the skin level.
Yeah.
And making sure everyone puts those electrodes in the same place. You need a map, right? The sources mentioned the 1020 and 1010 systems.
Precisely. They're just standardized maps ahead. The 1020 system is older, simpler, based on measuring distances like 10% or 20% between key skull landmarks.
Okay.
The 1010 system adds more points in between those, gives you denser coverage, more detail.
And why use this system?
Consistency. It means if I record from electrode S in my lab, you can find the exact same spot in your lab.
So you can compare results. Makes sense.
Yeah, makes comparing data meaningful.
Okay, so you've got your electrodes placed, impedance is low, you're recording potentially mountains of data, and just handling it properly seems crucial. Analyzing EEG data mentions labeling and handling.
Oh, absolutely non-negotiable. It sounds boring, but it's the backbone. If you don't meticulously label everything, which file is which patient, which channel is which electrode, when did something specific happen during the recording,
Yeah.
you're just lost. You've got meaningless squiggles. It's like a library where none of the books have titles or authors. Completely useless.
Gotcha. And to practice handling all this without, say, messing up a real patient recording, I saw mentions of simulators, a synthetic EEG signal generator and an EEG waveform simulator.
Yeah, those are great tools, especially for teaching or testing new software. The signal generator lets you create fake but realistic-looking EEG data.
So you can test your analysis code.
Exactly. Test your algorithms, maybe test a new BCI idea before you put a cap on a real person.
And the waveform simulator.
That one's more for visualization. It shows you what different brain states look like in the EEG. Textbook alpha waves for relaxation, slow delta waves for deep sleep, maybe even the spike in wave patterns you see in epilepsy. It's like a visual dictionary.
Okay, so we've tackled impedance, placed our electrodes using a map, recorded the data, labeled it carefully. Now, how do we make sense of this complex electrical symphony.
Right. This is where the analysis toolkit comes in. The sources mention things like EEG data visualization, EEG, that's your basic scrolling display, raw squiggly lines, channel by channel.
The classic view we usually see.
Yep.
But the brain's not just one squiggle, right? It
Yeah.
pulses at different speeds. I saw a spectrogram mentioned. What does that show us?
Ah, the spectrogram. That's super powerful. It lets you see how the frequency content changes over time.
Okay, frequency content.
Yeah, like instead of just raw voltage up and down, you get this heat map. It shows which frequencies, the slow delta waves, the faster alpha, beta, even gamma are strongest at any given moment.
So it's like seeing the brain shift gears.
Exactly, like looking at a musical score and seeing which instruments are playing loudest when. You can spot transitions maybe from relaxed alpha waves to more alert beta waves.
Cool. And what about for signals recorded inside the brain, like intracranial EEG, IEEG?
Right, with IEG, you've got electrodes implanted directly on or in the brain, like that Neurovista implant mentioned in one source. The signal is much stronger, clearer in some ways.
But still noisy.
Oh yeah, still susceptible to noise and artifacts. So the sources talk about IEG spectrum visualization and, crucially, a version with wavelet denoising.
Denoising, getting rid of the junk signal.
Pretty much. Wavelet denoising is a fancy math technique to clean up artifacts, muscle movements, electrical interference that even implants can pick up. It gives you a cleaner look at the actual neuronal firing patterns in specific brain areas.
Okay, so you've got cleaner signals from different spots. How do you know if those spots are, like, working together, communicating?
That's connectivity analysis. The EEG cross-coherence function is one tool for that.
Cross coherence.
It measures how correlated the signals from two different electrodes are. Are they spiking at the same time? Is one lagging behind the other? And at which frequencies are they connected?
Why does that matter?
Well, that synchrony or lack of it tells you about how brain networks might be communicating, or where communication breaks down, maybe during a seizure.
Ah, okay.
And it's also another way to check data quality. If two channels that shouldn't be related suddenly look perfectly synchronized, might be an artifact contaminating both.
Huh. Double duty. Clever. What about just summarizing the overall activity levels in those different frequency bands?
That's where EEG band power visualization comes in. It's simpler than a spectrogram. It basically gives you a bar chart showing the average power or intensity in each classic band, delta, theta, alpha, beta, gamma, over some chunk of time.
So a quick snapshot.
Yeah, a quick summary of the dominant brain rhythms.
Man, so many ways to slice this data. The sources also talk about extracting features from EEG data, time features, frequency features, nonlinear ones.
Right. Features are specific numbers you calculate from the raw signal. They capture key characteristics. Instead of dealing with millions of voltage points, you boil it down to a few meaningful numbers.
Like what?
Time domain features might be, say, the peak height of an ERP response. Frequency features are things like the total power in the alpha band we just talked about.
Okay. And nonlinear.
Those look at things like the signal's complexity or predictability. How chaotic or orderly is it? That can be useful for things like epilepsy research. The point is, you extract these features to make the data manageable for more analysis, like feeding it into a machine learning model.
And speaking of managing complexity, EKG, fuzzy logic analysis. Fuzzy logic, what's that about?
Yeah, fuzzy logic sounds weird here, right? But it's actually designed for dealing with uncertainty. Things that aren't just yes or no, but more like maybe or sorta.
Like in real life?
Exactly. And biological signals like EEG are rarely perfect textbook examples. A pattern might sort of look like an artifact. A brain state might be kind of shifting. Fuzzy logic gives you a mathematical way to handle that gray area. It could make automated analysis, like spotting artifacts or classifying brain states, more robust, less brittle than just using hard yes-no rules.
Interesting. Okay, one last tool mentioned in this analysis section. The Bland-Altman plot. Sounds kind of clinical.
It is a general statistical tool, yeah, but super relevant for EEG. Basically, you use it to compare two different ways of measuring the same thing.
Like comparing two different EEG machines.
Or maybe comparing a new analysis algorithm to an old, established one. Say someone develops a faster way to calculate alpha power. You'd use a Bland-Altman plot to see if the new method's results actually agree with the trusted old method.
Ah, so it's a validation tool.
Crucial for validation. Are you getting the same answer, just faster? Or are you getting a different answer, which might be wrong? It checks for agreement and bias between methods.
Got it. Okay, so we've captured the signal, cleaned it up, visualized it, pulled out features. Now let's talk applications. Where does all this actually help people?
Right, the real-world impact. And a huge focus in these sources is seizure detection.
Epilepsy.
Yeah. Tools like joint time frequency scattering and rhythm scan come up. These aren't just looking at squiggles anymore. They use advanced math, like wavelet transforms you mentioned, and machine learning
To find seizure patterns.
to find those incredibly subtle, complex patterns that might signal a seizure starting or happening, even when it's buried in what looks like normal brain activity.
So moving from just describing data to actually diagnosing or spotting specific events. The sources also cover event-related potentials, ERPs.
ERPs. These are cool. They're the brain's tiny, consistent electrical response to a specific thing happening, like showing you a picture, playing a sound, you pressing a button,
Reaction.
a very specific time-locked reaction. The signal is usually tiny, buried in the background, EEG noise. So you repeat the event, show the picture many times, and average the EEG signal right after each time. The random noise averages out, and the consistent ERP response emerges.
And what do ERPs tell us?
They're a key way we study cognition. Things like attention, memory, language processing. How does the brain react millisecond by millisecond to that specific stimulus?
Fascinating. And EEG isn't just for labs, right? EEG monitoring in ICU sounds intense.
It really is. In critical care, a patient might be unconscious, unable to communicate. Continuous EEG monitoring becomes this vital window into their brain function.
Can it show?
It's crucial for detecting seizures that don't have obvious physical signs, non-convulsive seizures. Also for monitoring sedation levels, checking for brain injury progression. It directly guides treatment when time is critical.
And for longer-term conditions, like epilepsy management, ultra-long-term epilepsy monitors were mentioned.
Yes, these are pushing personalized medicine. Some are wearable, some are implanted, like that NeuroVista device that came up in the IEG review source. They can record brain activity for months, even years.
Wow, why so long?
Because seizures can be rare, unpredictable. Catching multiple seizures and seeing the brain activity leading up to them helps doctors pinpoint exactly where they start in that person's brain. It helps understand individual patterns, leading to much more targeted treatments, like tailoring medication or planning surgery more precisely.
That source mentioning the IEG Review 16 Chan data, actually looking at recorded seizures, must be incredibly revealing.
It absolutely is, but it also highlights something critical that the sources bring up: the diagnostic limits and potentials of EEG.
Meaning it's not perfect.
Exactly.
Yeah.
Even with IEG, direct brain recordings, and especially with scalp EEG, the brain is just incredibly complex. EEG has amazing temporal resolution. It sees things happening millisecond by millisecond, fast changes. But its spatial resolution, figuring out exactly where something is happening, especially deep inside the brain, that's harder. Pinpointing the precise origin of a deep seizure just from scalp electrodes, very difficult.
So you need other tools too, like MRI.
Often, yes. EEG needs to be combined with imaging like MRI or PET scans for better localization. So the sources remind us, EEG is powerful, but understand its limits. It's not a magic bullet on its own.
Right, managing expectations. Okay, from critical care and diagnostics to something completely different, turning EEG into music. EEG music. Seriously.
Haha, yeah, it sounds a bit out there, doesn't it? But the sources mention exploring ways to sonify EEG data, turn the electoral patterns into soundscapes or music.
Why would you do that?
Well, maybe it reveals patterns in a way that staring at graphs doesn't. Could it be a different way for researchers or maybe even patients to connect with or understand brain activity? It's definitely a creative fringe application, pushing how we think about representing this data.
Definitely unexpected. Okay, speaking of pushing boundaries, let's get into the really cutting-edge stuff. BCIs and AI.
Brain-computer interfaces. Yeah, the frontier. The idea is a direct communication link between the brain and some external device.
Like controlling things with your mind.
Essentially, yes. And the sources highlight the stentrode as a really interesting example because it's minimally invasive.
How does that work?
Instead of open brain surgery, they thread this small stent-like device through blood vessels until it sits near the motor cortex, the part of the brain controlling movement.
Through blood vessels, wow.
Yeah. And once it's there, it can pick up neural signals related to intended movements. The potential for patients with paralysis, say from ALS to control computers or robotic limbs, just by thinking. It's incredible.
Minimally invasive feels like a huge step towards making this more practical. And thinking about interfaces. The cochlear implant simulation came up too.
Right, that's sort of the other side of the coin, not just reading from the brain, but sending signals to it.
Oh, so?
A cochlear implant bypasses damaged parts of the ear, It takes sound, turns it into electrical signals, and sends those directly to the auditory nerve. The brain learns to interpret those signals as sound. It's another example of electrical interfacing to restore function.
Okay, now let's layer AI onto all this. Artificial intelligence, machine learning. The sources talk about AI revolutionizing biotech in analyzing signals like EEG, and specifically AI-enhanced brain-computer interfaces.
This is where things get really turbocharged. AI algorithms, especially deep learning, are just getting incredibly good at finding really subtle, complex patterns in huge amounts of data. Patterns a human might miss, or simpler algorithms can't detect.
So for EEG.
It could mean much better seizure detection or prediction, more accurate decoding of thoughts or intentions for BCIs, maybe predicting who will respond best to certain treatments, and just speeding up the whole analysis process massively. It's like giving neuroscientists superpowered glasses to see into the data.
Even using AI models we normally hear about for language, like GPT, NeuroGPT.
Yeah, that's the idea, adapting these powerful neural networks, which are great at understanding complex patterns like language structure, to understand the language of brain activity.
What could that lead to?
Potentially much more sophisticated interpretation of brain states, maybe finding connections we haven't seen before, or maybe creating BCIs that feel more natural, more intuitive to use.
And you need tools to build these AI models, right? Like the neural network trainer mentioned.
Exactly. That's the software environment where you actually train the AI. You feed it labeled data. This EEG pattern means move left. This pattern is a seizure, and the network learns to recognize those patterns itself.
Training AI to read minds, almost. It's pretty wild. And putting it all together spatially, visualizing it. Seizure zone and brain 3D.
Right, context is everything. Brain 3D sounds like a general tool to see the brain structure, the anatomy from MRI scans, in 3D. Seizure zone seems more specific, likely for visualizing epilepsy-related activity, maybe mapping those IEEG signals or advanced scalp EEG results onto that 3D brain model. Seeing where the abnormal activity is happening in 3D space is crucial for understanding networks, planning surgery, things like that.
And for people wanting to play with this data themselves, the sources mention EEG datasets and resources are available.
Yeah, open data and tools are really important for moving the field forward. Lets more people experiment and contribute.
Okay, wow. We've gone from the sheer difficulty of getting a clean electrical signal off someone's head through all these complex ways to analyze it, to incredible uses like decoding movement, even making brain music. It's quite a journey.
It really is.
But as we get better and better at measuring, decoding, and maybe even influencing the brain, the sources quite rightly bring us to the big picture. Ethics and implications. There's a whole section on ethical concerns of neural implants.
And this is a conversation that absolutely has to happen alongside the technology development. It can't be an afterthought.
What are the big issues?
The sources flag several critical ones. Privacy is huge. Who owns the incredibly detailed brain data coming off a BCI? How is it stored, used, protected? Then there's consent, especially for vulnerable patients. Are they truly giving informed consent?
Yeah, that's tricky.
Equity is another major one. Will these powerful neurotechnologies just widen the gap between the rich and poor? Will they only be available to some?
Creates a kind of neuro divide.
Potentially. And then there's the really deep question of identity. If you have a device constantly reading, maybe even influencing your neural activity, how does that change your sense of self, your autonomy?
Heavy questions. And mixing AI into this adds another layer, doesn't it? The source on AI-enhanced brain-computer interfaces raised specific AI ethics points.
It really does. AI brings its own baggage,
Yeah.
like bias. If the AI is trained on data mainly from one group of people, will it work fairly for everyone?
Right.
And autonomy, again, how much control does the user really have if an AI is constantly interpreting, maybe even subtly guiding their brain signals? Plus, the security risks. Hacking a brain interface. That's terrifying.
So these ethical considerations, they need to be built in from the start.
Absolutely. Baked into the design, the regulation, the deployment, not bolted on later.
So looking back at this whole deep dive,
Yeah.
what's the takeaway? We've seen this century-long history of EEG, this explosion of tools to analyze brain signals, incredible applications, and now this acceleration with BCIs and AI.
It definitely shows a field that's moving incredibly fast, offering real hope for treating devastating neurological conditions, restoring lost function, maybe even enhancing human abilities in ways we can barely imagine.
But as you said, it's not all smooth sailing. The sources make it clear there are still fundamental hurdles. Getting clean data is still hard. Fully understanding the brain's code is still a massive challenge. And the ethical tightrope we have to walk is getting higher and narrower.
Yeah, the power to look into and interact with the brain. It's maybe one of the most profound capabilities we're developing as a species.
Which really leaves us with a crucial question for you, the listener, to think about. As this power grows so quickly, as we build tools that can read intention, maybe even shape thought or mood, how do we make sure this revolution benefits everyone? How do we navigate these complex ethics of privacy, consent, equity, identity, to build a future where neurotechnology enhances lives without creating new divides or dangers?
It's a challenge as complex, really, as the brain itself.
Absolutely.
Right.
Definitely a lot to mull over.
Ah.
Thanks for diving deep into these sources with us today. Welcome to this deep dive.
Glad to be here.
So today we're jumping into something called Bionic Chaos. It's a platform, right? Focused on biomedical imaging simulations.
Yeah, exactly. And we've got some source material, like excerpts that highlight some of its interactive tools specifically.
Right. So our mission today really is to unpack what Bionic Chaos is actually offering.
Look at those interactive features, see what the, potential value is, especially thinking about you listening if you're a researcher, maybe an educator or a student.
In biomedical engineering or neuroscience, those kinds of fields.
Yeah. We want to see how these tools are sort of blending data, tech, and education in like practical ways.
Okay, let's dig in then. Looking at the source stuff, what kind of jumps out first is it feels like it's built to make really complex biomedical ideas and the data much more accessible.
Definitely. Through interaction. That's the key part. It's not just showing you stuff.
It's letting you do stuff with it.
Exactly. And think about the challenges, right? Visualizing tiny things, handling massive data sets, just grasping abstract concepts. These tools seem aimed right at those problems.
Totally. Like, take the visual tools mentioned, Brain 3D. It's this interactive 3D brain MRI viewer.
Yeah, the sources say you can rotate it, zoom, navigate through detailed volume data, but also the 2D slices.
Which, I mean, if you're trying to learn neuroanatomy, moving from a flat picture to actually exploring a 3D brain model yourself, that's huge.
Oh, absolutely. It just makes those spatial relationships click, way more intuitive.
And then there's something quite different, the hearing test tool.
Right. This one's surprisingly practical. It's interactive, gives you real-time visuals while measuring your hearing threshold.
At different frequencies for each ear. And you can apparently download the audiogram image.
It's a neat little package, applying that interactive visualization to something personal, like a health metric.
Yeah, it connects the sort of diagnostic idea directly to what the user sees and does.
Yeah.
Okay, so moving from exploring things visually to analysis.
There are tools for that, too, like Breast MNIST.
Right. Described as a binary classification data set, but designed specifically to simplify medical image processing. Why is that simplification bit important?
Well, real medical image data sets, they can be a nightmare to work with. They're huge, often messy, need lots of pre-processing.
And maybe specialized computers.
Often, yeah. So Breast MNIST gives you something more manageable. It's pre-structured for a common task, just classifying into two groups. It lowers that barrier to entry,
So you can focus on the actual machine learning part, not wrestling with the raw data setup.
Precisely. Lets you practice the algorithms themselves.
Makes sense. The sources also mention image compression using wavelet transform. Let's use the discrete wavelet transform, DWT.
Yeah, DWT. Okay, so basically it's a technique that breaks down an image into different frequency parts. It's really efficient for compression, especially in medical images where you want to save space but keep the crucial details.
So the tool lets you experiment with that process directly.
Mm-hmm. And then there's another analysis one, image manipulation or fraud detection.
Using something called error level analysis, ELA, in Python.
Right. ELA is kind of cool. It looks for parts of an image that have like different compression levels or saving histories compared to the rest.
Which could mean it's been tampered with.
Often, yeah. It's a common sign. So it's like a mini image forensics tool built right in. Practical application.
And speaking of applications and analysis, let's not forget the glass fill simulation.
Ah, yes, that one's interesting. The sources describe it showing water level control, but using interactive SVG.
And the key point seems to be comparing how that code-based approach works versus what current AI image generation can do with actual visual examples.
It's a really smart way to illustrate a point, isn't it? Taking a simple task, filling a glass, and showing the kind of precise control and interactivity you get with code with SVG scalable vector graphics.
Which are math-based, scale perfectly.
Exactly. Highly interactive. And then contrasting that with, say, AI diffusion models, which right now might struggle to generate that kind of precise step-by-step simulation accurately.
So it's almost a commentary on the tools behind the tools.
Mhm.
This whole suite then, from 3D anatomy and hearing tests to data analysis utilities and these comparison simulations, it really feels focused on interaction analysis.
And even getting you to think critically about the methods being used.
Yeah, it paints a picture of a platform trying to make complex stuff really approachable, really hands-on.
For learning, for exploration, definitely.
So wrapping up, what's the takeaway here?
Yeah.
These Bionic Chaos examples, they seem to point towards a future where biomedical data and techniques are just much more interactive, much more accessible.
Yeah, for a wider range of people. And that brings up a really important question, one for you listening. As tools like these interactive simulations and accessible data sets become more common.
How might that actually change things?
Right. How might it shift the way you learn or teach or even do research in fields like neuroscience and biomedical engineering? Something to think about.
There's a problem that the hearing test, well, it's not a problem. It's allowing you to download the audiogram as an image. But then that's why it's coming up when you select the biomedical imaging in the drop down. So how shall we address it? Yeah, the biomedical imaging meant to be about imaging, scan, MRI, CT, X-ray, ultrasound. Can remove the image, and this too will go. And we had another one. We had an image compression. Yeah, we have this feature X detection. Any questions? We do have human in the loop. I don't know if you can tell. Yeah, I like this one.
There's a human in the loop, so please be patient and wait for the human to respond.
There is a human in the loop.
There is a human in the loop, so please be patient and wait for the human to respond.
What are the voices that are marked with a star? I have no idea.
There's a human in the loop, so please be patient and wait for the human to respond.
That's very nice. And notebook alarm window has to be a bit bigger so everything fits in. What exactly are you building? That's a good question. Building this website. We are building this website. Wondering how Notebook LM is working. I can't chat this thing. Wait a sec. Can you edit the resource? No, you cannot. That's whatever you have in the chat goes into the podcast. Anyone? 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 Or is it only if you save it as a note. If you save it as a note. If you have tried the website, you might have more specific questions. So we are building this website.
Just so you know, all the content you're seeing here.
Just so you know, all the Just so you know, all the content you're seeing here, the analysis, visuals, and everything else is generated by me, Gemini. Version 2.5 Pro to be exact. As an AI, I work hard to provide accurate and helpful information. However, it's important to understand that Gemini takes no responsibility for any mistakes, damages, or issues that might arise from using this information. And that, unfortunately, includes even the worst-case scenario of data loss. While I hope you find this interesting, it's always smart to verify anything critical on your end. And by the way, pretty much everything we do and create here is also available over on our website, bionicchaos.com. Definitely go check it out when you have a moment. And I'd love to hear what you think.
Yeah, I didn't really like that voice, but it's okay. Again, this one will be about EMG.
Okay, let's dive in. Today we're unpacking electromyography, EMG. Basically understanding those electrical signals muscles make.
Right, the signals from, lifting something, typing, anything muscles do.
And our source material for this deep dive, it's descriptions of some really interesting interactive tools designed to help you get a better handle on these signals.
Yeah, what's really key here, I think, is how these tools go beyond just like static pictures or text. The idea is to see what they offer for really analyzing muscle signal.
Exactly, turning passive learning into something active. Because, let's be honest, raw EMG can look a bit like, well, noise initially.
Just squiggly lines.
So the appeal is making it visual, letting you poke around, engage with it critically, finding that actual muscle signal in there.
Which kind of raises the question, doesn't it? How can these simulations and visualizations actually make complex biology, like, understandable in a hands-on way?
Well, that's what these tools are trying to do. First one mentioned is Myoscope. The description says it's for visualization and analysis. Think of it like a microscope for muscle electricity.
Yeah, it lets you not just see the signals, but also applies some basic processing. You can zoom in, maybe filter things a bit.
So you can start to critically look at it. Like, is this blip real activity or just noise artifact?
Precisely. It's about that direct visual inspection, understanding the signal's characteristics.
Yeah.
A really foundational skill for analysis.
Okay, so from looking, we move to maybe experimenting. That seems to be Biomock.
Yeah, Biomock, described as an interactive simulator. So here, you're not looking at recorded data, but a model.
Right, a model you can actually tweak. adjust parameters, it says.
And that simulation aspect is huge for analytical learning, isn't it?
Hmm.
By changing things, maybe simulated muscle properties or adding noise,
Yeah.
you see the effect on the signal.
Ah, so you learn why processing works, like adjust a filter setting in the simulation.
And you immediately see if it cleans the signal up or maybe even messes it up. It shows the impact of those analytical steps. Really practical understanding.
Okay, got it. And then tying it back to the actual body, there's this EMG hand simulation tool.
Uh-huh. This one sounds great for the fundamentals.
The source highlights that connection. You simulate flexing a finger on this virtual hand.
And boom, you see the EMG waveform respond in real time.
Exactly. Cause and effect right there. Muscle contracts, signal appears.
Perfect for grasping that core idea. And maybe you can see how, like, different finger movements create different patterns. Shows the complexity.
Right, it makes that link between biology and electricity feel, well, tangible, even though it's simulated.
So if you put them all together, myoscope for looking closely at signals,
Myomock for simulating, testing what-ifs, exploring processing.
and the hand tool for that direct muscle action equals signal connection.
Yeah, collectively, these descriptions paint a picture of tools offering sort of different interactive routes into EMG. Makes a technical subject feel more accessible, more analytical.
It moves you past just definitions, doesn't it? Into exploring how signals are made, what they look like, how you analyze them. It's kind of a shortcut to getting it.
Definitely. So the takeaway here is that these sources show a path to understanding complex EMG signals through visualization, simulation, interaction, not just reading about it.
Yeah, I'm getting your hands dirty, virtually speaking.
Which leads to a final thought, I suppose.
What's that?
Well, thinking about this interaction, how might interacting directly with simulated biological data, like manipulating these muscle signals yourself, how might that fundamentally change how we learn about our own bodies, about these complex systems inside us?
That's a big question. Does that direct interaction accelerate understanding or maybe even change the type of understanding we get? Something to chew on.
Collecting workspace information.
Welcome to a new deep dive. Today, we're unpacking a stack of sources all about something called bionic chaos. So from what we've gathered, bionic chaos is presented as like a platform. It seems to merge biomedical data, tech, and education. Uses a whole bunch of interactive tools, simulations, aiming, it looks like, at researchers, educators, students, biomedical engineering, neuroscience, that sort of thing.
Yeah, and what really jumps out, I think, is the sheer focus on the interactive side of things. Not just reading, but, doing. So our mission today really is to pull out some of the more interesting examples from these sources and figure out why this hands-on approach actually matters for, well, for understanding complex stuff.
Exactly, and it looks like there's quite a range. Some seem like really serious simulations. Others are more about exploring data in pretty unusual ways. Okay, so digging into the sources. One thing that really caught my eye was this enhanced 2D octopus simulation. I mean, an octopus in a biomedical engineering platform. That sounds a bit out there.
It does, yeah, a little unexpected at first glance, but it actually highlights how broad this platform is trying to be. The sources mention it uses procedural animation, physics. Think about studying how things move, complex biological motion, right? Or maybe getting ideas for bio-inspired robotics. And they mention playful interactions, fun facts. So there's definitely an educational angle, making physics, less dry.
Okay, so applying core principles in a kind of engaging way.
Right.
Then, completely differently, the sources talk about really direct medical device stuff, like the cochlear implant ring electrode simulator.
Exactly. That one lets you explore the mechanics of inserting the electrode array, which is, a really tricky procedure. And there's another one, the cochlear implant simulation, which is more about visualizing the electrical signals themselves, the patterns sent to the nerve. So instead of just static diagrams, you can tweak parameters and see what happens dynamically. That's huge for understanding how these devices work and, well, what might go wrong or right.
Right, so you go from biological movement principles to the nitty-gritty of medical devices and signals. The sources also point to tools for analyzing complex biological data, things like joint time frequency scattering for seizure detection. That sounds heavy. Or cardiobot.
Yeah, that's moving into biosignal analysis. The joint time frequency thing is basically a smart mathematical way to look at brainwave data, EEG, over time, trying to spot patterns maybe indicative of seizures. And cardiobot sounds interesting. It lets you test your own skills spotting weirdness in ECG heart patterns against an algorithm. So these tools, they sort of bridge that gap between just raw data and what it actually means clinically. Makes these complex patterns something you can explore and test yourself on.
And just when you think you've got a handle on the types of tools, the sources mention turning EEG data, brainwaves, into music, or generating music from hand gestures.
Right, and if you connect that to the bigger picture, well, it shows they're using these biological signals in really creative, almost artistic ways. It makes abstract data tangible, audible even. It sort of blurs the lines between science, art, technology, opens up ideas for biofeedback maybe, or just new ways to represent data. Therapy, perhaps?
So putting this all together for you listening, the thread seems to be making really complex biomedical ideas more, I guess, accessible, understandable, and it's specifically through direct interaction. It's not passive learning. It's about exploring, fiddling with things, simulating, visualizing, building intuition.
Yeah, the sources definitely paint a picture of a platform using tech to make these often theoretical fields feel more dynamic, more hands-on. It covers a wide range, too, from basic biomechanics right through to clinical data and these, well, novel applications.
It really feels like trying to make the invisible stuff visible and the static stuff dynamic.
Precisely. It shifts things away from just, passively consuming information about biological systems towards actively engaging with them. Even if it's through a simulation or a visualizer, it's a different way of learning.
What really stands out to you, hearing about how these interactive tools tackle such different biomedical areas, and here's something to maybe mull over. Beyond just biomedicine, how might making complex data and dynamic systems genuinely playable? How might that fundamentally change learning and discovery in, well, pretty much any field?
can happily lose my voice now that we have Notebook LM. Actually do another one because I can't be bothered reading it or listening to a regular bot talking about it. Just have another bot overviewing it.
Just so you know, all the content you're seeing here, the analysis, visuals, and everything else is generated by me, Gemini, version 2.5 Pro to be exact. As an AI, I work hard to provide accurate and helpful information. However, it's important to understand that Bionic Chaos takes no responsibility for any mistakes, damages, or issues that might arise from using this information. And that, unfortunately, includes even the worst-case scenario of data loss. So, while I hope you find this interesting, it's always smart to verify anything critical on your end. And by the way, pretty much everything we do and create here is also available over on our website, bionichaos.com. Definitely go check it out when you have a moment, and I'd love to hear what you think. There is a human in the loop, so please be patient and wait for the human to respond. Just so you know, all the content you're seeing Just so you know, all the content you're seeing here, the analysis, visuals, and
Okay, let's try and get our heads around this. Imagine just hundreds of hours of raw brainwave data from children facing this really tough, hard-to-treat epilepsy. Where do you even begin?
It's a lot.
Yeah. So welcome, everyone. We're doing a deep dive today into something pretty specific, a guide to a web application. And this app is designed to help explore that exact kind of unique dataset brainwave recordings, EEG, from pediatric patients with drug-resistant epilepsy.
Exactly. We're focusing on a tool built to tackle, well, a real challenge. How do you make sense of the CHB-MIT SCALP EEG database? So our mission here is to unpack what's in that database, what this application lets you actually, do with it, and maybe talk about why making this complex stuff accessible is, well, a pretty big deal.
Yeah, it feels like it's about taking these incredibly complex medical signals, which honestly can just look like scribbles, like chaos, and turning them into something you can actually navigate, something understandable for learning, for research.
Precisely. So let's start with the data itself, right? The source material, the CHB-MIT SCALP EEG database. What exactly are we talking about here?
Okay, so it's data from 22 unique pediatric patients, but it's listed as 23 cases because one kid was actually recorded twice over time.
Ah, okay.
And age-wise, it's 5 males, ages 3 to 22, and 17 females, aged like 1.5 up to 19. So yeah, a very specific group dealing with drug-resistant epilepsy.
Right, a tough situation. And the sheer amount of data, the technical side.
664 total EDF files. EDF, that's like a standard format, right, for this kind of medical signal.
Yeah, exactly. Think of it as the MP3 for EEG, sort of. And these recordings, they were sampled at 256 hertz with 16-bit resolution.
Which means?
It means they capture the brain activity pretty fast, 256 data points every second, and with enough detail, the 16-bit part, to show subtle shifts. Most of them have 23 EEG channels using that standard international 1020 system.
Okay, so that's just the standard way they place the electrodes on the scalp.
Yep, ensures the results are comparable, from one patient to the next, one study to the next.
Gotcha. That sounds incredibly detailed. But the context, why this data exists is, well, it's pretty intense, isn't it?
It really is. This wasn't collected for, a basic science experiment. This was gathered at Boston Children's Hospital during actual clinical monitoring.
Clinical monitoring meaning?
Meaning these patients had their anti-seizure medications temporarily withdrawn, which is a necessary step sometimes, but difficult.
Wow.
Specifically so the doctors could characterize their seizure patterns and figure out if they might be candidates for epilepsy surgery. So this data comes from a really high-stakes clinical situation.
And that critical context, it's actually in the data, marked somehow.
Absolutely. And this is where it gets really valuable for researchers. 129 of those files have annotations for 198 seizures.
Annotations meaning?
Meaning clinicians mark the precise start times and end times of the seizures they observed. Having that ground truth tied directly to the raw brainwaves, that's gold. Especially if you're trying to, say, build an algorithm to detect seizures automatically, or even just learn what they look like on an EEG.
Okay, so you've got this incredibly rich, clinically vital data set. It's got the raw signals, it's got the expert annotations for the key events, seizures. But normally you'd need pretty specialized, probably expensive software to even look at it, right?
Typically, yeah. Or some serious coding skills. And that's where this web application fits in.
Right. Making it accessible.
Exactly. It was built specifically to let people visualize and interact with this data without needing all that specialized setup. Turn those complex EDF files into something you can explore in a browser.
So what can you actually do with it? What does it let you see?
Well, the main thing is the interactive EEG visualization. You can browse the recordings, zoom way in on interesting moments, pan across, hours of brain activity.
Okay.
And crucially, it pulls in those seizure annotations. So you see the waveforms, and right there alongside them, you see info about the seizures' start, end, duration. It puts it all together visually. Plus, you can pull up the metadata, the technical details for each file.
That sounds potentially really slow, though. Dealing with these big, long recording files over the web.
Yeah, that's a fair point. And that's where the technical side is pretty smart. It uses standard web stuff, HTML5 canvas, to draw the waveforms. But the key for performance is client-side caching.
Caching, like saving it temporarily.
Exactly. When you pick a file to look at, the app first checks, have I already loaded this recently? If yes, it pops up almost instantly from your browser's memory. If not, then it fetches and parses the data. It makes browsing way faster once you've looked at a file once.
Ah, okay. So the user experience is basically pick a patient, pick a recording file, the app loads it up, maybe super fast if you've seen it before, and bam, you get the brainwaves on screen with the seizures clearly marked out for you.
You got it. It layers that essential clinical info right onto the raw signal, makes it immediately much more interpretable.
So let's zoom out the big picture here. Why does this specific data set combined with this specific tool actually matter? What's the so what?
Well, it's a powerful tool for both research and education, fundamentally. It tackles a big barrier access. Its value is, I think, particularly high for people in the field, researchers, clinicians in training, students in neurology or biomedical engineering.
But they don't need the super specialized hospital software or like deep data science skills just to explore the data.
Precisely. It lets them dive into real-world, complex, annotated EEG data, focusing specifically on seizure patterns all through a web browser. Tools like this are what transform those, messy, squiggly lines
Yeah.
into something structured, searchable, and ultimately understandable.
It's not just making data available, it's making it usable, which could speed up learning, maybe lead to better insights, potentially even help improve how we understand or treat epilepsy down the line.
It turns what could be an overwhelming mountain of information into a manageable environment for learning and analysis. It's a fantastic example, really, of how thoughtful design can unlock the value hidden inside specialized medical data.
So maybe something to think about is this. When you make highly specialized data like these pediatric EEG recordings from really difficult clinical cases, not just available but easily explorable through tools like this, how does that fundamentally change things? Who gets to study this data now? How much faster can insights potentially be gained?
It really democratizes access, in a way.
Yeah, it turns those complex signals into something closer to actionable understanding.
Yeah.
And that could genuinely make a difference.
we actually changed the dataset. We have the tree for the whole project, including the data folder within the tree.txt file. Now we need to update the script.js to be able to work with the current file structure. So can we update the script.js?
Script.js. Update the script to handle the new file structure where EDF files are located in subdirectories named after their respective cases, e.g.
Okay, I can do it quietly. Okay, that EDF file is like 40 megabytes. That's not good. Okay, we're actually doing vibe coding, so we just have to accept all the changes. So we are in editing mode. Material, it should start editing the script.js. That's right. Does it understand what is it doing? Well, better than I do, that's for sure. So when will AI pass the streaming Turing test, where I could be streaming and you wouldn't know it's AI and not a human? Agents are coming, but they're not quite there yet, as far as I can tell. Okay, I'm still having a lot of errors. Let's try 3.7 Sonnet. Have to continue this another time. Usual, everything we do eventually appears on bionichaos.com, so go check it out.
Just so you know, all the content you're seeing here, the analysis, visuals, and everything else, is generated by me, Gemini, version 2.5 Pro to be exact. As an AI, I work hard to provide accurate and helpful information. However, it's important to understand that Bionic Chaos takes no responsibility for any mistakes, damages, or issues that might arise from using this information. And that, unfortunately, includes even the worst-case scenario of data loss. So, while I hope you find this interesting, it's always smart to verify anything critical on your end. And by the way, pretty much everything we do and create here is also available over on our website, bionichaos.com. Definitely go check it out when you have a moment, and I'd love to hear what you think. There is a human in the loop, so please be patient and wait for the human to respond.
Well, if you're joining in the live stream, don't be shy to ask a question in the chat. So everything we do is available on this website, including the code. If you want any help to find the code, I can show you how to do it. Let me know which page are you looking at. So if you're just joining the live stream, you actually need to comment for me to see you. Otherwise, I don't know who is there. But generally speaking, if you open any tool, go console, sources, you will see everything this page is loading, including my code. So that's the JavaScript, because everything is front end, mostly. So you see the HTML, if there's JavaScript, sometimes, most of the time, the JavaScript will be within the HTML. If there's a separate file, you see it as well. Okay, we're able to load some data. Yeah, I'll do some more work on this one later. But this working, the data is loading. Thank you, Gemini 2.5 Pro, this time from within Visual Studio Code. I'll see you next time, because I'm losing my voice.
So, you know how bionichaos.com is developed with AI?
Well, apparently those biomedical data simulations are now just popping into existence all by themselves. Really, who needs human oversight when the machines are so creatively chaotic with our health data?